Hello, welcome to session 4 in the series Analog Circuit Design using ADS. In this series I'm going to talk about the devices, and the device which I have covered earlier in the section is a diode, and what I'm going to do is I'm going to talk about diodes and MOSFETs, and I'm going to talk about the the physical construction of the device and its characteristics. So we know that a diode is usually drawn like this. This side is the anode, this side is a cathode, and this is going to be p type and this is going to be the n type. Okay, so this is the diode which we know from the treatment which we had in the last session. Physically this diode is slightly different. Okay, so let's say we consider the N-well CMOS process. So in an N-well process, okay, the diode can sit in its N-well, right? So what would be that diode? So just 1 second. Okay, so let's say that this is the N-well in which the diode sits, and this region is P minus. Okay, so this region is P minus. Okay, and this is the N-well, and inside this, okay, so this is going to be N. Okay, and then you are going to have a P plus, and then you can have N plus. Okay, so now this one, okay, and then there is going to be N plus over here. So let's mark this N plus like that, and P is basically this. Okay, so there are two contacts over here. Okay, so this is going to be the anode, this is going to be the cathode, and this is going to be the body terminal. Now this is N plus for a reason. Okay, what can happen is when you form a junction, right, so you don't want the metal to be interacting with the semiconductors. So the way to do this is a heavier doping on the N plus. So that's what N plus is, a body terminal, right? So now if I want to reverse bias this PN junction, right, so then this N has to be connected to VDD. So the diode becomes a 3-terminal device rather than a 2-terminal device, right? And here the connection of the body is to VDD, and this would be connected to the most negative terminal, that is going to be the ground. So this is what happens in the N-well process. Now there is another diode which will sit outside the N-well, so let's look at that one. Okay, so in that case you have got P minus, okay, and so everywhere there is P minus, then you have got N, okay, and then you have got P terminal, right? So now what is going to happen is there is going to be a P plus here, and this is all P minus. So let's just shade this out. Okay, so this is all the bulk is, right? So this body terminal is connected to the most negative, right? So in that case the diode would look like this. You have an anode, which is a p-type side, and then you have a cathode, and then you have a body terminal which will be connected to ground. So in this case the body terminal would be connected to ground, and so now this whole substrate is grounded, and you can make these contacts, Okay, these are called substrate contacts. You are going to make these contacts all around the device, right? And then you have got this as anode, this as cathode. So this is going to be your device, okay, which is sitting outside the well, right? Now this diode, okay, is going to have some advantages over this one. The diode, this diode has an advantage that the leakage currents are going to be smaller here. Leakage currents are smaller because it sits in its well, while in this case it is sitting outside the well, so the leakages from this diode are going to be more. So there are going to be two ways to do this, right? If it is sitting in the well, right, then your VDD is the body terminal. If it is sitting outside the well, then ground is the body terminal. So it's a 3-terminal device. Now we have come to a point where we derived Q for a PN junction. That was basically twice of Q epsilon xi 0 plus VR times of NA ND divided by NA plus ND raised to half. Now let's assume that ND is very large. Okay, so it tends to infinity. In that case, this Q is, I would address as QB, is equal to twice of Q epsilon xi 0 plus VR times of, if you take ND in denominator, then all you will be left with NA raised to half. So this is the charge in case one of the side is a metal, right? Okay, or N-type is basically a metal, not N-type. Or same situation happens in case of a MOSFET also, right? So we will next talk about a MOSFET. So let's look at the structure of a N-channel MOSFET. Okay, so this MOSFET, this process is an N-well process. So the NMOS device sits in directly into the substrate. So when that happens, then what do you have? You have got a gate. Okay, right, so the gate basically is it's a polysilicon, silicon dioxide, right? So this is a gate, and then the polysilicon is non-conductive, right? So you basically implant the top portion of this, and this becomes a conductive poly. So this forms a gate terminal. So once you have a gate terminal, okay, then what you do is you can implant with, so this, to the wafer to start with is P minus, right? So now you can implant regions around the gate, okay, and the channel would be formed by the gate itself, right? So this kind of process is known as self-aligned process, right? So you have this portion which I am going to call N plus, okay, and these terminals are interchangeable. They are source and the drain, right? And besides that, there is another terminal which will be P plus, and then you will be interfacing this contact which is body. So now this is an N-channel MOSFET. Okay, so what do I see here? I see that this MOSFET has got 4 terminals rather than 3 terminals, right? And let's put those 4 terminals as S stands for source, then there is D stands for drain, and then you have got gate, and then you have got the body. Okay, so let's see what each one does. Source, as the name says, it is going to source, it is the source of majority carriers. So it sources majority carriers into the channel. Okay, that's why it is called a source. Drain would drain majority carriers from the channel. Majority carriers from the channel. Okay, so that's why they are called source and drain. And gate basically gates, okay, or rather controls the flow in the channel, right? Gate controls the flow of carriers in the channel, and body, okay, is for isolating the devices. From substrate. Okay, let's see one by one what is happening over here. So it doesn't matter, I'm going to draw this again. So you have got a gate, and let's assume that initially I have all the terminals, so this is basically n plus MP minus. Okay, so initially, so let's say this is source and this is drain, and let's say there is a body terminal over here. Okay, initially let us connect all to ground for the sake of just understanding. Okay, so when you connect this to ground, there is a PN junction here. So there are two PN junctions. One is source in the bulk, and then the drain in the bulk. So this is going to have a certain depletion region. Now P minus means that this depletion region will be wider, and over here also there is going to be depletion region, and there is going to be depletion region on the other side, but it is going to be very narrow because this is n plus. N plus means the dopant density is large. Okay, so this way the device is isolated from the substrate, okay, or bulk P minus. Now let us do one thing. Let's assume that I have a certain source to body voltage here. Okay, so let's say this is ground, and this is going to be a voltage between source and body. So this is plus minus, and we call this as VSB. Now for the operation of the device, I am going to assume that this is also sitting at VSB. Okay, so this is also sitting at the same VSB. So everything would be relative to S, and right now there is no horizontal field because VSB, because there is no potential between source and drain, right? So basically this is sitting at a potential which is VSB above the ground. Now in this scenario, okay, what I do is I apply a certain gate voltage. Okay, so I apply a certain gate voltage with respect to source, right? So this I will call as VGS plus minus. Okay, when I do that, what's going to happen is this is a silicon dioxide. The gate is silicon dioxide, right? So it has got dipoles. So let's say these are dipoles, and I am drawing the blown up picture of the gate, right? So what's going to happen is this is the conductive portion of the poly. Okay, so if I apply a positive voltage here, then the dipoles are going to align this way, plus 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 plus, and this causes the electrons to escape from source and the drain and form a small layer underneath. Okay, so as I keep increasing the, so over here there will be the source, and over here there will be the drain. So as I keep increasing VGS, okay, so as I keep increasing VGS, what's going to happen? Okay, this depletion region this depletion region is going to remain same, but here it is going to widen. Okay, so basically this depletion region, this widens, and then you get a small layer of electrons below it. Okay, now when the density of these electrons, so let's say that is basically Ne, becomes comparable to or much larger than Na, then the portion of semiconductor underneath the gate, it inverts. So it's no longer a p-type, it becomes an n-type. This happens when the potential is greater than twice of the built-in potential. Now if you remember, the built-in potential is kT over Q ln of Na Nd over Ni square. So basically Nd and Ni cancel out, you will have a Na over Ni in this case. Okay, so when this potential is more than this plus it's more than the work function, semiconductor metal work function. So what is the work function? This is the potential which is required to free this or to pinch off these electrons from nearby N plus. Okay, so if this potential is large enough, then these electrons are going to move in and will be supplied by both the sides, by source and drain, to form a channel underneath. So that potential is known as the semiconductor metal potential, metal work function, plus the twice of built-in voltage, plus it has to overcome this charge. So the potential due to this charge is going to be equal to QB by COX. Okay, so it has to overcome that QB by COX. Now you can also have an implant here of negative ions here, so as to adjust the threshold voltage, so which I can write it as minus QSS by COX. This will be equal to the threshold voltage. When the gate to source voltage, when VGS is greater than this voltage, then there is an inversion under the gate, or a channel is formed between source and drain. Now if you keep increasing VGS but your VDS is 0, then this channel will keep on increasing. It will keep on increasing in the channel depth will keep on increasing, but the charges will not flow. For the charges to flow, you will have to apply another field. So you have got one field which is basically a vertical field. Then if you have a channel formed, to make the electrons flow, you need a field in this direction which will be horizontal field. So the operation of a MOSFET is based on two fields. One is basically gating it, which is a vertical field, and the other one which is causing the drift current, which is the horizontal field. So this field is because of the VGS and this field is because of VDS. Okay, so let us draw again what happens when I have a channel and applied VDS. Okay, so you have got a gate and then you have a conductive poly gate, and this is what the gate is. Okay, so now I am going to apply a potential. So this potential I am going to keep as VGS with respect to source, and the source is like this. So this is the source terminal and this is plus minus VGS. Now this is going to set up a vertical field. What about the horizontal field? I am going to have another potential here. This is VDS plus minus, and this is connected to the drain terminal, right? Okay, so in this scenario, okay, the channel would have appeared for VGS greater than VDS, VGS greater than VDS, sorry, VTN. So channel would form, and then when you apply VDS, okay, then what is going to happen is there is going to be a flow. Now let me give some dimensions to this. Okay, So let's say that this is y equal to 0 and this here is y equal to L. So I have an axis. Okay, so on this axis I have y, right? So y equal to 0 over here and y equal to L over here, right? So let us consider a case where this potential is applied VDS, right? Now, so VGS has to be greater than VTN for the channel to appear. Now, let us assume what happens when we apply VDS. So when we apply VDS, the net potential across the channel would be over here on the source side, it will be VGS minus VTN. Okay, so the net potential, okay, will be VGS minus VTN. So let's say it's over here. This is VGS minus VTN. So let's say VGS minus VTN is a quantity. Okay, so VGS minus VTN is a quantity, V overdrive. So the net voltage over here is a V overdrive, and then I have DS subtracting from this, right? VGS minus VTN, and then we have the net voltage I'm plotting, right? So this is the maximum over here because VDS is equal to 0 here. So the net voltage is basically VGS minus VTN minus V of Y. It's a function of Y, right? At Y equal to L, the VDS, the voltage which is applied drain to source is VDS, and at Y equal to 0, okay, so this is Vy. At Y equal to 0, this is going to be equal to 0. Okay, so the net potential across the channel is going to be VGS minus VTN minus VDS, right? So over here it will be like this. Okay, so let me draw this again. Okay, so at any point the voltage is going to be equal to VGS minus VTN minus Vy, and at this voltage over here, it will be VGS minus VTN minus VDS. Okay, now when this voltage is applied, the channel is going to be thicker over here and it's going to be thinner over there, because the net potential on the source side is more than the net potential on the drain side. If you see, net potential on the source side is more than the net potential on the drain side, so the channel is going to be deeper at the source and it is going to be shallow at the drain. Now if you keep on increasing, okay, if you keep on increasing the VDS, then there would come a point where it will be doing like that. Okay, so that will occur for a condition that VGS minus VTN, okay, minus VDS becomes 0 at the drain. So when this happens, this channel disappears. So it is no longer a pentagon. The channel, if I was to draw here as the channel would look like this. It has pinched off from the channel has pinched off from the drain. Sorry. So channel has pinched off from the drain. Or rather, let's draw bigger so that don't worry, we'll draw these lines again. So I'm exaggerating the thickness here. Okay, so that you know what's happening. So the channel has pinched off over here. Okay, so this is referred to as pinch off. So this is referred to as pinch off. So when pinch off occurs, right, the channel is detached from the drain. Okay, this happens at VGS minus VTN is equal to VDS or equal to V over drive. So that's the point when the channel is detached. Now if you keep on, so the total length of the gate is L. Now if you keep on doing this, increasing VDS, then the detachment point will move to the left, right? And then there would be a modulation of the length. So this is delta x. So the length has become L dash L minus delta x. So this is referred to as channel length modulation. Now let us find out what is a, so up till now what we have done is we have figured out when the channel is formed. So when VGS is greater than the threshold voltage VTN. So we have done threshold voltage. Okay, and this threshold voltage is this quantity. Next is we are going to look at the current. Okay, so we are going to look at drain current, and we are assuming for this treatment that the channel is already formed. So we are assuming VGS, sorry, so we are assuming VGS is greater than VTN by V over drive, or VGS minus VTN is equal to V over drive. So at that point what's happening is, okay, so we are having treatment for that. So at that point what's happening, let's see that. Okay, so let's derive this. Okay, so to derive this, we know that the charge in the channel is given by, so I'm going to ignore all the charges, okay, all the signs. So it will be simply COX times of VGS minus VT minus VY. So this is the charge. Okay, and then if I was to do consider a dimension which is going to be going into the paper, right, or basically we can draw this like in 3D like this. Okay, so in 3D the device would look like this. Right, so in 3D the device would look like that. Okay, so this dimension is called the width, right? So the total charge will be width times that times of the velocity, which is going to be this, would be equal to the current ID. Okay, so now let us see what is this velocity. This velocity is mobility times of the applied field. I'm ignoring all the signs, and this field is going to be equal to the divergence of, or sorry, the grad of V. So in this case this will be basically dVy over dy. Again I'm ignoring the signs here. Okay, so let's substitute everything back. So in that case the drain current will be equal to mu n COX times of W times of VGS minus VT n minus of Vy, okay, dVy, and we'll take this differential to the left hand side, dy. Now if I integrate this, okay, from 0 to L, id times of dy is going to be integration from 0 to vds times of mu n cox w, okay, vgs minus vtn minus vy times of dvy. Okay, so if I integrate it, now the analogy goes like this. Let's say I have a tube connected to a tap which is which is supplying water to the garden. Now if I pinch the tube, the amount of water which is flowing through the tube is not going to change. It's just that the pressure with which it comes out is going to change, right? So similarly, the current will not change, okay, depending on how much the channel is pinched. So in that case, this id is independent of this integral 0 to L dy, and this simply will be id into L would be equal to, right, this integral mu n cox is constant, vds, so this integral will be vgs minus vtn minus vy, and I am going to have this as a square divided by 2, and there will be a minus sign, so I will be inverting the limits. Okay, so this is what I'm going to get. So next is id is going to be equal to mu n c, okay, so there is one w here, so id is equal to mu n cox by 2 w by L into this. So now this will be equal to vgs minus vtn square minus of vgs minus vtn square plus of twice of vgs minus vtn times of vds minus vds square. So this term would cancel out. So all I am left with is that the drain current would be equal to mu n cox by 2 w by L into twice of vgs minus vt times of vds minus vds square. Now what is this equation? This equation is of a parabola, right? And so if I was to plot this drain current versus vds, okay, so if I have drain current on this side and if I have vds on this side, so this side I have vds and this side I have got drain current, correct? Then at smaller value of vds, this term would be 0, the second term would be 0 because it's vds square. So at very low values of vds, the id and vds are the linear functions, so it will grow linearly and then it will become the parabolic in nature, and at certain point of time the pinch off occurs. So the pinch off is going to occur somewhere. So let's draw this again. Okay, so at some point in time the pinch off will occur. So otherwise if pinch off doesn't occur, right, then the relationship goes like this. So if I was to plot the relationship as per this equation, this is going to be like that. Now at pinch off, this equation at pinch off, this equation is not valid anymore, okay, and the current is supposed to become a constant after the pinch off, right? So the current is supposed to become constant after the pinch off, right? And this value would be equal to IDS, which is equal to, okay, the peak value. So to find the peak value occurs at VDS equal to VGS minus VT, where the pinch off takes place, which is equal to V overdrive. So at V overdrive, this would happen, right? The pinch off will occur. But beyond pinch off, what's going to happen is that L is going to shrink to L dash, and as you increase VDS, L dash is going to become smaller and smaller. So the same equation with L dash instead of a L. Okay, instead of a L, you have L dash. So in this region, the current is going to
increase like this, and then something like this would happen. So now this region, okay, so this region, okay, is called the triode region. Okay, and this region is called the saturation region after the pinch off. Okay, so what's happening in the triode region? There is a certain region where this is linear, and beyond that there is a square nature, and when it hits the maxima, there the pinch off occurs. After that the current should become constant, but it increases because of the channel length modulation, right? So that's the, now this is for a given VGS or a given V overdrive, right? Given VGS or V overdrive, right? Now if I change VGS, I will get different set of curves. So for example, if I reduce VGS, I will have the same thing, but it will do like that. Okay, so once it has done this, okay, after that it should become flat. So basically this has happened over here, and this should become flat like this, but this is going to do this. Now notice that this slope for VGS 1, the slope is more than for VGS 2. Now this is because, okay, so 4 overrides small. Okay, okay, so now this is because when VGS is less or V overdrive is less, then we are talking about a different slope here. Sorry. Versus this. Okay. So now what is going to happen is, uh, first of all, the channel with a smaller VGS, the channel is going to be less deep, and the channel is less deep, then delta X is going to be less. Because of that, if you are going to have a smaller VGS, this slope is going to be smaller, right? And if you were to extend this, okay, so if you were to extend this, right, and if you were to extend this one, they are going to meet at a point on this axis itself. They are going to meet at a point on this axis. Okay, so that would be referred to as early voltage VA. Okay, so all these are going to meet at a point, early voltage VA. Now, so this is the nature of output current versus output voltage. So this is referred to as output characteristics. Okay, so this is referred to as output characteristics. Okay, so now this equation is valid. This equation is valid only for the triode region. Now for at the pinch off, the equation would be IDS is equal to mu NCOX by 2 W by L, and twice of VGS minus VT into VGS minus VT. So we are substituting this over there. So we will be left with VGS minus VTN square. Okay, so if I was to plot ID versus VGS minus VTN square, okay, so that would be just joining these points. So basically that will be just joining these points, and this will be the square nature, right? Okay, so that would be that. Now beyond this, what's going to happen? beyond this, ID would be equal to IDS times of, okay, now if there's going to be a slope involved, right? 1 plus, okay, lambda times of VDS minus V over drive. So if lambda is the slope, then slope times of VDS minus V over drive. So what will be VDS minus V over drive? So let's consider VDS at this point. Okay. So in this case, this distance is VDS minus V over drive. Correct? Times the slope will give you this quantity. Correct? Right. So that's the total current. It will be IDS plus lambda times of VDS minus V over drive. Okay. So having said that, okay, so this would be in the saturation region. Okay. So let's mark them. What there are three equations for current. This is the triode region. Sorry. This is the triode region. This is the pinch off. And this one is the saturation region, where you are going to see channel length modulation. So this is the channel length modulation component, right? Now, this gives rise to what is called the output impedance. Okay. So now, if for example, length was large, then delta x in a large length. So let's look at this. If the length was large to start with, this if L was large, so delta x compared to L was a small percentage. So you would see that as L increases, then the slope will reduce. So slope is a function of L, right? And okay, also the slope is a function of the current, right? So or you can say VGS, right? It's a function of VGS or current. Okay, so for smaller currents or smaller value of VGS, the slope is less. For larger value of VGS, the slope is more, right? Okay, so that into account, we can say that the output impedance is the reverse of this slope, right? So if I was to write here output impedance RDS, yes, this is drain to source resistance, is equal to 1 over lambda times of IDS, right? Uh, okay, rather 2 over, okay, times of 1 divided by 1 plus I0 divided by VDS minus V over drive plus phi 0. Okay, so what is means? It means the following. At pinch off, this number is going to be 0. So at pinch off, this number is going to be 0. This number is going to be 0 at pinch off. In that case, this would become approximately equal to 1 divided by lambda times of IDS. So at this point, the slope is going to be like this. But if you go further away, the slope is more, and this is because as this increases, right, this increases, then this number is no longer 1 plus 1. It is going to be 1 plus some small number, right? So in that case, it will almost become twice. So in case of pinch off, RDS is equal to this at pinch off. But if you go much higher VDS, then RDS will be equal to approximately equal to twice of this. Okay, so what does it mean? It means that if you are operating somewhere in saturation, the output resistance is much higher than if you are operating at threshold or at sorry at the pinch off. Right, so the two slopes you can mark here also. In every curve you can mark two slopes. So in this quiz, the slope is like this, but if you go far away, the slope is like this. So this is referring to a higher resistance than that. So the output resistance is going to be this. Now let us see what is lambda. Lambda is equal to KDS. It's a proportionality constant divided by twice of L of root of VDS minus V overdrive plus 5. Okay, where KDS is a proportionality constant. So now what does it mean? So let's see what it means. Okay, it means that what I'll conclude. One, at pinch off, okay, output resistance is than smaller than well within saturation, right? It's smaller than well within saturation. So this is one conclusion we have. Second thing I want to conclude is uh, RDS, okay, goes up if you bias down the transistor or if your overdrive is small. So RDS is going to be large. Okay, and this you can see in this curve, right? So this slope and this slope, the slope for VGS2 is smaller than slope of VGS1, or the inverse of slope is the resistance, right? So that's it. Okay, next thing you will observe is that if lambda, okay, is small, so when will the lambda be small? The lambda would be small if L is equal to large. So the third point is if L is large, if L is large, then delta X, delta X would be much smaller than, so delta X will be much smaller than L. Okay, so when this occurs, then RDS is going to be large. So that means that if you check a device which is a long channel or L is large, then the output resistance is there. If L is small, delta X is much larger in percentage of L, then the output resistance is there. So if you make a device which has a shorter length, the output resistance is going to be lower. Okay, so having said that, okay, so that comes from here. Now KDS is a function of uh, KDS is going to be equal to twice of epsilon over QNA, okay, where Na is the channel doping. So if Na is large, KDS is small, lambda is small, RDS is large, which means that if you heavily dope the channel, then delta X is going to be smaller because you know the heavier dope portion has a smaller depletion region, right? So that's rationale goes in here. If Na is large, then the channel length modulation is going to be small and the output resistance will be large. So the fourth thing which I want to write here is if Na is large, then RDS is large. Then RDS is large. So the output resistance is a function of length, a channel length. The larger the length, the larger the RDS. Is the function of overdrive. Okay, smaller the overdrive, right? larger would be the RDS, or smaller the drain current, larger is the RDS. And then if you are biased right at the pinch off, the resistance is going to be less, almost half of the the resistance when you are well within saturation. Okay, so that's it. And the last part is if the channel is more heavily doped, then delta X is small, and that causes the output resistance to go up. So this is what we have learned from output characteristics. Now, if you see this blue curve here, okay, this is IDS versus VDS. Now, if I replace, so if I was to draw IDS versus VDS, it goes like that. I would write here IDS is equal to mu NCOX by 2 W by L VGS minus VTN square. So this is a square law nature, right? So let's see that square law nature. Okay, so that sorry, so that square law nature is visible over here. Sometimes it's so difficult to move. Okay, so if I was to plot ID or IDS versus VGS minus VT, then this would be a parabola like this. This is the square law nature. Now, if I was to plot it versus VGS, if I was to plot versus VGS, then it will shift by VT. So this would be VT, and you will have the same curve here. Correct? So this would be called the transfer characteristics. So that is output characteristics, and this is going to be transfer. Okay. So what do we learn from this output characteristics and transfer characteristics? Little more into transfer characteristics. Okay. Let's draw this again on this page. Sorry. So I'm going to draw. Okay. So this distance is VTM. Okay. So if I consider region far away from VTM, so this is VGS, and this side is IDS. Okay. So if I was to go far away, then what is going to happen? This VDS doesn't exist. Okay, so in this case, the the field, the horizontal field doesn't exist, right? So you have the gate, and you have got the source and the drain, right? And VDS is very small. Sorry, VGS is very small. So what's going to happen is the channel is barely there. So channel is not there. So if channel is not there, this is like an NPN transistor. It's just that the P is very large. So it doesn't matter. It's still say NPN transistor. So if it's as an NPN transistor, then there would be a current in this region. Okay, so that is known as subthreshold current. Okay, So subthreshold current. So there is no inversion at this point. Now, if I was to introduce an inversion here at this point, there is a strong inversion beyond this point. But then there is another reason here, there is a moderate inversion. So basically you are going to have three different places. Okay, one would be weak inversion, the other one will be moderate inversion, and the yet another would be once you have crossed this is a strong inversion. Okay, so usually we operate these devices under strong inversion. But if you operate it under moderate or weak inversion, these transistors are going to have very large GM, which is comparable to that of an NPN transistor, because truly this is still an NPN transistor before the saturation occurs or before the inversion occurs. So it's a NPN transistor. So GM is going to be large. Okay, not GM, sorry. Beta is going to be large. Or okay, so So you can take very large devices and operate them over here for some reason. So for example, noise consideration will be there, right? So you may take very large devices. You can make a very, you can make a low noise amplifier. Okay, operating the devices at very low current densities and very large devices. So usually that happens when you do with the medical or implantable, circuits. Okay, so this is the transfer characteristics. Now, what do we extract from this transfer characteristics, right? So if I take this slope, okay, so this slope will be dou IDS over dou VGS. This will be equal to the GM of the device or transconductance, or the slope is the transconductance. So you just take this, and if you differentiate with respect to VGS, your answer would be mu n COX. 2 will go away, W by L into V over time. Okay, so this can also be written as uh, twice of okay, so if I multiply with 2 and divide by 2, this will become a current. Okay, so ID is divided by V over time. So that would be the relation. So this is the transconductance of the device, the slope of this transfer characteristics. That's called transconductance. Right, and what will be the unit? Ampere per volt, no, because it's a slope, right? Usually it will be in microamperes per volt. Okay, so that is the GM of the device. What else do you get from this transfer characteristics? VT, right? Now let's say, what do you get from the output characteristics? You get the slope as the output resistance, inverse of the slope. And then one more thing is there, what is happening in this region? So if I was to take this region, why the current is picking up? The current is picking up because the drain to source voltage and the drain and the bulk junction, the drain bulk junction breaks down. So when the drain, this is the drain bulk junction. When this breaks down, all the current basically leaks to the substrate rather than going this way. Okay, so this is the major cause of the breakdown. That's why you are going to have a LD MOS, right? LD MOS would reduce this current, leakage currents. Okay, so this region is basically drain to bulk breakdown region. Okay, so this is the output characteristics. Now, if the channel length becomes very small, you start seeing what is called the short channel effects, right? So I am going to cover that short channel effects in the next lecture. So we have something called short channel effects. Okay, 6 or 7 of these effects are there, which we are going to cover in the next tutorial. So I'm going to stop here for now.